I'd like to welcome everyone to the second lecture in the inference conference on plot theory and related topics. Our speaker is Professor András Némethi from the Rényi Institute, and he will give two lectures. The first one today, the topic is Lattice Cohomology.
Thank you very much for the invitation and for the opportunity to speak at your conference. And so my topic is the lattice cohomology associated with known as surface singularities. Maybe at the end I will speak also about other dimension, about the curves and about higher dimension. So this lattice cohomology is somehow the motivation and also how it started and how I will present somehow for the surface case. It's a bridge between the topology, low dimensional topology, and algebraic geometry or analytic analytic geometry. So the analytic invariants of isolated singularities and topological invariants of isolated singularities. These will be connected, and somehow we define new cohomology series. The motivation was that I wanted to understand analytic invariants like the geometric genus or cohomology of line bundles on the resolutions. And I wanted upper bounds or even in some nice topological upper bounds. And even in some cases when the analytic type is nice, say weighted homogeneous or rational or elliptic or some nice constructions, then I wanted to characterize analytic invariants by topologically. So like say Artin characterized in the rational case the Heegaard Floer function and such topological characterizations. Here we want similar topological description or at least bounds for analytic invariants, and that's why we try to connect somehow the topological invariants and analytic invariants. And so let's start what was actually the most important. So how we start the series. I want the beginnings to introduce some invariants. So maybe I show you this one here. That the analytic and topological, so we want some kind of, we put in parallelism this object. So it's in the analytic case, we start with an isolated complex singularity, and from an analytic point of view, they are characterized by the local algebra. And in the topological sense, so if it's isolated, then I can consider the link. And so we embed somewhere in some C to the n, and we consider a very small ball, as a very small sphere around the origin, around the singular point. We take the intersection, and that is a transverse intersection, and that will be oriented, connected, closed Riemann-manifold. And basically that characterizes completely the topological type, since the X inside of that ball, it's a real cone over the link. So topologically, the link is complete characterization. So that is what we want to connect. We want this manifold, this oriented compact manifold, and we want the analytic type, say the local algebra or anything with analytic, what we can define using the analytic algebra or the local germ. At the beginning, I will concentrate on the dimension 2. So that means that this is a complex, and the analytic type is a complex. Even I can assume normal, but it's not necessary. Isolated surface singularity. And in that case, the link is a oriented, connected, closed Riemann-manifold. So this is here at the right-hand side. I would like to apply, say, low-dimensional topology techniques of the, or at least intuitively to have some intuition or to some models of the low-dimensional topology, and in the right-hand side we want analytic invariance. Of course, sometimes the bridges or the correspondence is not easy. For example, if I define on the right-hand side something using the fundamental group of the link, say the Casson invariant or the Casson-Walker invariant, it's not so easy to have its analog or to make a, say, reformulation in terms of the algebra. But this is somehow our goal. So let's see some technical notation. Everybody knows what the resolution is. I consider a good resolution. I consider the exceptional curve, and that is the irreducible decomposition of the exceptional curve. EV they are the irreducible exceptional curves. In the X tilde is the resolution. And combinatorially, they are described or codified in the resolution graph, or I can consider also just the lattice. Yes, the lattice in my case will be H2 of X tilde. That is, these are generated freely by the exceptional curves. So that is exactly the rank is how many exceptional curves we have. And here we have the natural intersection form, and that is, we know that that is negative definite intersection form. In general, the determinant is not plus minus 1, but it's non-degenerate. And in this talk, I will assume that the link is a rational homology sphere. So that means that the rationals of the first Betti number is 0, or the first H1 over Z is finite. And from the point of view of the resolution graph, this means that the gamma is, so I have a tree of pi ones. So that is somehow, it's an assumption a little bit, it's easier, the discussion in this case. So let's see what is our question or our starting point. So if I start from the topology, so again, the link is a 3-manifold. It's an oriented 3-manifold, compact 3-manifold. Close manifold, and so recently we have a lot of nice invariants, also numerical invariants. The Kelsen in the case of integral homology spheres, or the Kelsen-Walker invariant in the rational homology spheres, or the Seiberg-Witten invariant. But even we have a lot of cohomology series, the Heegaard Floer theory of Oswald and Szabo, or the embedded contact homology, or we have the monopole Floer homology of Koheimer and Mrovka. So we have beautiful and very, very strong invariants, topological invariants associated with the 3-manifold. And the question is that how we understand all these, say, topological invariants in the language or in terms of the singularity theory. Can we connect say, the older or classical singularity invariants with these ones, or even more importantly, if they have any analytic interpretation, or if they interact with analytic invariants, or actually the point is that the main goal is to define their analytic analogs. Yes. So in general, when we have a normal surface singularity and we have exactly this bridge between topology and analytic invariants, we try to find pairs of invariants. Analytic invariants, we try to pair with topological invariants. And so what is the meaning of the topology? So basically, if I fix an analytic invariant, like say the multiplicity or the Hilbert sum function or the geometric genus or some line bundles, say cohomology of line bundles on the resolution, I would like to understand that if in case of nice analytic structure, I have some topological candidate, which for nice analytic structure topologically describes the corresponding analytic invariants, or at least bounds again. If I have, say, for the geometric genus, the optimal upper bound in terms of the resolution graph. And of course, that here the question is rather interesting, because if I fix a topological type, of course, that we can have many actual big moduli of analytic structures. And of course, I know, but I don't know if it's known. Actually, I know that it's not known, the analytic, so moduli space of all the analytic structures. But we have some parameter space, and we have some understanding of this parameter space. What we ask here is not completely this analytic, say, classification, but say a stratification of the analytic structures, and to understand, say, the analytic invariants, how they modify when we change the analytic structure, and how we can say relate with topological invariants. So here, actually, let's start with some concrete invariants. I start with the Seiberg-Witten invariant, and the Heegaard Floer of Oswald and Sabo. Heegaard Floer has many versions. I will not enter very much in the definitions, but actually we know that in the last decades, this was a very important part of the loaded dimension topology, and still is very active and very interesting. So the question is, what are the analytic pairs of these invariants? And so as a starting question. And so let's see a little bit, still I want to say a little bit about the structure of the Seiberg-Witten, how they are not defined, but how they are associated with the link. So I have the three manifold link, and we consider all the spin C structures of the link of the oriented three manifold. And actually we know that this is an H1 LXZ torso. So this H1 is the first homology, integral homology of the link. This is by our assumption, because the link is rational homology sphere, this is a finite abelian group. And we know that the spin C structures, it's an H torso. So that means that their cardinality basically is the same. That is important. Actually, in this case, we have even a canonical spin C structure. So any spin C structure basically can be computed in terms of the canonical spin C structure by this action. H cross, here I have H cross sigma canonic. So that is, all the spin C structure can be generated in this way. So let's understand a little bit more about the H1. So we have the lattice L that is generated freely by the course of the exceptional curves. That is H homology, H2 homology, and we have the dual lattice, the dual of H cohomology, or the relative homology also. We can consider also in this way by duality. And L embeds in the dual lattice because the form is non-degenerate. And actually, the quotient is by the long exact sequence of homology is this H1 of the link. So actually, if the intersection matrix is unimodular, the determinant is plus minus 1, then actually L is L prime and H is trivial. Otherwise, if depends the number of elements, is exactly the determinant of the intersection matrix, and that is exactly the number of spin C structures. So what is the point here? That the Seiberg-Witten invariant, it's for each spin C structure gives a rational number. So that is somehow an invariant. So I want to say, if I want an analytic analog, then I would like to create somehow an invariant which is indexed by the spin C structures, or it's indexed by the first homology of the link. For the Heegaard Floer, here I choose the plus version because that will somehow fit with our lattice cohomology. Actually, it's multi-grading. The first grading is exactly, it's a direct sum corresponding to the spin C structure. So each spin C structure provides an HF plus associated with the link and the spin C structure. And each term HF plus associated with sigma, it's a Z-graded and it's a ZU module. So it has a very, very interesting rich structure. Actually, I have a Z-grading and also a U action. The degree of U is -2. Yes. And also we have some kind of Euler characteristic notion, like for any cohomology theory. A little bit later, I will define for the lattice cohomology. And the Euler characteristic of the Heegaard Floer is the Seiberg-Witten invariant. So that is, say, some kind of recall a short, or say a few words about the Seiberg-Witten invariant and the Heegaard Floer theory. But the main question for us is that what is the analog? What is the analytic pair? So of course, at the beginning, I will start here with the Seiberg-Witten invariant. So I want to somehow to see if what is the analog of the Seiberg-Witten, and after that we put the question for the cohomology theory. So let's go back a little bit. What is the simplest analytic invariant of, say, of a normal surface singularity or on an isolated singularity is the geometric genus. Yes. So in this case, so if I take the analytic type and I take a resolution, then of course X tilde is smooth, and I consider the structure sheaf, and I consider the first homology of the structure sheaf, and that is the definition of the geometric genus. Here, the higher HIs are 0. So this is really this H1 somehow dominates, or that plays the role of the top class or something like this, local top class. Well, this is just a number, and I would like to extend. I would like to have an H-indexed invariant, like was the Seiberg-Witten, which was indexed by the spin-C structures, or like an H-torsor by the H1 of the link. So this is H1 of the link, and now I would like to extend this PG, or define somehow an extension which is indexed by this finite abelian group. So what do we do? Because this H1 it's finite, I can consider at the level of link, of course, that I can consider the universal abelian cover. So pi1, we project on H1, and that has a kernel, and that provides unramified regular covering, but also on the regular part on x minus 0, we will have a regular covering. By classical theorems, actually, that can be extended to a singularity. So this means that we have a normal surface singularity XA covers, it's a Galois H covering of X in such a way that on the regular part is a regular covering, and it's branched, say, at the origin. So that is also irreducible, and we have a local singularity, the universal abelian covering, with a Galois H action. And now we can repeat at the level of universal abelian covering the definition of PG. So here it's H1 of X tilde of the universal abelian covering. And on that, HX. And H is a finite abelian group. So this has a eigenvalue decomposition corresponding to the characters of H. So H hat is, this is the Pontryagin dual. Actually, in this case, we can identify H is H dual using the intersection, the non-degenerate intersection for. Here is the formula, the theta identification, because yes, H is how I told you that is the dual lattice divided by the lattice. So I take a representative, say L prime in the dual lattice, and then using this exponential expression, we associate to any H element the character. And then in this way, some of the characters can be identified with H, or we can stay also with the characters, no problem. So then each eigenspace has a dimension. They are indexed by H. So that is somehow H index extension of the geometric genus. This is called the equivariant geometric genus of the normal surface singularity, whose link is a rational homology sphere. So that somehow we have no, at least numerically, an analytic invariant, which is H indexed. And in general, that is what we do. If we want, because in the topology, anything is basically, most of the invariants are indexed by the spin-C structures. Here, the corresponding, say, extensions indexed by H, we do using the universal abelian covering. We go to the universal abelian covering, we take the invariant of the universal abelian covering, we take the H action, and then we will have the H index invariant. So let's see what we can do now with this invariant. So let's put in pairs. So on the left-hand side here, I have the analytic associated with the analytic type of X. We have the equivariant geometric genus, so it's indexed by H. We have these numerical invariants. On the right-hand side, we have this link, and we have the spin-C structures indexed by H, and we have the Seiberg-Witten invariants. And that's the point, that it's not just it's not incidental. So it's actually in many cases they agree, and we even formulated the Seiberg-Witten invariant conjecture with Nicolaescu, and in some cases we proved, and then actually with Nicolaescu we formulated only for the canonical spin-C structure, and the equivalent version later I extended. The point is that here we have equality for many nice analytic structures. So for example, is a weighted homogeneous analytic structure if I take on the left-hand side, and the link then is a Seifert-3 manifold on the right-hand side, then the corresponding equivalent geometric genus coincides with the Seiberg-Witten of the Seifert-3 manifolds. This is true for rational singularities, for elliptic singularities, for Spice-Gaussian singularities of Neumann and Wall. For many nice singularities, this equality holds. Actually, the conjecture was that this is true for any Q-Gorenstein singularity, and actually that is not true. It was too optimistic, that conjecture. Even for hypersurface super isolated singularities is not true, this identity, because in that case somehow the PG makes a different choice, different part of the Seiberg-Witten. Maybe later I will explain this when we know the lattice cohomology, that which PG, which part of the lattice cohomology choose. So it's an interesting choice. But anyway, here we have some kind of candidate. We have some kind of pairing that somehow the Seiberg-Witten, I hope, or we hope, that behaves from topological point of view, at the point of view of the link. We have the pair, the geometric genus, which behaves from analytic point of view in similar way, or we hope that we will have some parallel series. So what is now the, let's go back to the main question, what we asked at the very beginning, that the categorification. So the topological side, we have the Seiberg-Witten, and there is the Heegaard Floer, or the monopole cohomology of Cohen and Oka. So we have homology series, yes, of the link of the three manifold, such that their Euler characteristic is the Seiberg-Witten. So we have here, they are indexed by the species structures, they are graded ZU modules, beautiful theory. The question is that what is the analog of it? So do we have a cohomology theory, exactly again, indexed by H, yes, and for each H or for each species structure, I have a graded ZU module in such a way that the Euler characteristic is the geometric genus. So that is exactly our wish. Yes, and also we would like to have something which actually reflects some of the analytic structure. Also the PG, it's a good invariant. Actually, if I move the analytic structure with fixed topological type, PG might jump. So that's already sees the variation or the modification of the analytic structure with fixed topology. Where we would like to have even better invariant, somehow cohomology theory, which is not just a Euler characteristic level measures analytic structure, but even it's better. So that is the goal. Actually, we will do this in two steps. Actually, historically, that was happening. That the first step was actually a topological cohomology. So again, at the left-hand side here, I have the Heegaard Floer and Euler characteristic go with the Seiberg-Witten. What I defined at some point, it's 15 years ago, and then yes, and I wrote a lot of articles about this. And this is the lattice topological lattice cohomology of the link. So again, that is, it's topological, is associated to the link, similarly as the Heegaard Floer or those other cohomology series. This is also indexed, or it's graded by the species structures, and each startup is a graded ZU module, and the Euler characteristic is the very same Seiberg-Witten. The definition, of course, is completely different. I use the resolution graph, the topological, so the combinatorics of the resolution graph. And even that they are isomorphic or not, a little bit later I will explain. And in the second step, then using this construction of topological as a model, we try to define, to extend, and find an analytic version, which is completely parallel theory. We want a cohomology theory whose Euler characteristic is the geometric genus. So the construction it's very similar if we somehow find the right model. So that is the combinatorial setup. We define the cohomology, lattice cohomology, and we will see that what is the definition and what exactly we need to define. And if this general definition, if I apply in some context, then I get the topological lattice cohomology. In the different context, if I define, then I will have an analytic. For a different, yes, there's some freedom in the choices, then I will have the analytic lattice cohomology. So what is the combinatorial lattice cohomology? So what I need is a lattice. Actually, it's basically lattice points I need, not really the linear structure of the lattice, just some kind of lattice points in R to the S or something. So some lattice say, but what is important that I fix a basis. So just to remind you that in the case of resolution graph, we have the lattice generated by the exceptional curves, and we have somehow very canonical basis by the exceptional curves. But here, just very general lattice and fixed basis. And also I need a weight function. So for each lattice point, I want an integer. And that should have some finiteness property that for n very, very small, I don't have values. So that will be empty, the inverse image of n. And for any minus, so it's all the lattice points below the weight below n, I have only finitely many. So just to have a good intuition for these conditions, let's go to the topological case that if I have the lattice of the exceptional curves, and then if I consider this Riemann-Roch function, yes, expression of that is the intersection form, yes, the parentheses and L intersected with L plus K, K is the canonical class, that is and the negative sign in front. So yes, that is the Riemann-Roch type expression. Here, the intersection matrix, the dominant quadratic part is negative definite, with the negative sign is positive definite. So if I'm thinking about as a real, say, that is a real definite quadratic function, if our reals. But of course, here I have to apply for the lattice points. If I have these ellipsoids, in the finite ellipsoids, of course, that inside of an ellipsoid at level n, I have finitely many lattice points, and we have all these finiteness properties. But what we consider here just again, lattice, fixed basis, and the weight function with some conditions like this, some finiteness condition. And out of this, I want to construct the lattice cohomology. So what is the construction? We consider ZS, actually we embed ZS in R to the S as a lattice points, yes? And in the R to the S, we consider all the cubes, that we have the cubical decomposition. So the zero cubes, so the 0 cubes are exactly the lattice points, like here. The 1 cubes are exactly the segments. Here it's very important, the choice of the basis. So exactly, then 1 cube it's an L and L plus in some direction. So for example, this segment. So L plus some base element. So these are the 1 cubes, and we have the 2 cubes again. That is just L plus EB, L plus EU, and L plus EU EB. So we have a natural cubical decomposition and very naive, of course. And the cohomology of this cubical decomposition, if I'm just taking usual cohomology, gives nothing, gives the cohomology of R to the S. But the point is that I have to introduce the weight function. That will give the difference. So here again, I want to emphasize that the EV choice is important. So otherwise, we will have longer, so different base elements provide completely different cohomologies here. Now we define also the weights of the arbitrary cubes. That is the maximum of the weight of the vertices. So for example, the weight of a vertex is just the weight of the vertex. But if I take a segment, the weight of the segment is the max of the 2 endpoints. If I take a square, then I take all the endpoints and the max of all the vertices. So it's rather arithmetical. This definition, usually if I want to run even for the Riemann-Roch function, it's not so easy to handle all these weights. Let's see what we can do with this. So again, for each cube, yes, each cube, we have a weight function. Yes, here it is. And then I consider, I take for any n, we consider the space Sn, the union of all the cubes in such a way that the weight of the cube is less than n. So what is the meaning of that? That if, for example, this is like, assume that this is like a quadratic function. So if I fix n, if a lattice point is inside, so it has weight less than n, I take it. If the other one is less than n, I take it. If it's out, the weight is higher, then we don't consider in a set. If I have a segment and both endpoints have weight less than n, then I take the segment. Also for a 2 cube, if all the vertices have a weight less than n, we take the 2 cubes also. And in this way, we consider we will have a cubical complex which is finite by the finiteness properties, complex, so basically topological space. Of course, that we can think that, okay, for example, in the Riemann function, that was a quadratic function, and then these are ellipsoids, but of course, this is ellipsoid over the real space, as a real ellipsoid is contractible. But how the lattice points fit and they are compatible, say, with the level sets of the quadratic function or level sets of the weight function can be very interesting, can be very complicated. So it's not, actually it's not true at all that these spaces are contractible. They have very, very interesting, very complicated topology. They might have very complicated topology. On the other hand, so for each n, I consider Sn, then I take a bigger n, then I get a bigger space because I take all the lattice points with weight less than n plus 1, n plus 2. So we will have a tower of spaces. So this tower of spaces is the most important object in this case. Yes. So that is what we would like to understand. So just to give a hint that why they are not contractible, just imagine that here I have this situation, what I have here. These lattice points has weight, say 0, weight 0, and here say weight 1, they are outside, and they cannot be connected as in Sn because these, you see, the one-dimensional segments, they don't belong because this endpoint has higher weight. So, for example, in this case, S0 or S associated with this situation has two connected components. But even one loops we can have. For example, if I have this situation in, yes, say rank 3, I'll make here the picture, and these lattice points have weight 0, but these lattice points here outside have weight higher, say 1, 2, 3, something. Then this has weight 0, weight 0. Then also this segment has weight 0 because it's the maximum of the ends is weight 0. So we will have here also these segments here. They are in Sn, but I cannot put any of the two faces. We cannot put because this endpoint is outside. So we will have here, say, a one-dimensional loop, which is not homological 0, say inside of Sn. So the Sn might have, and when we have rank is higher, say I have a resolution graph with 100 vertices, the rank of the lattice is 100, then we can have here, and then somehow the lattice points and the level sets are not very nicely compatible, then Sn, of course, can be very complicated. For example, and let's say that, for example, for the towers. So if I have, for example, I take the S0 level, then I will have here something, and they are not in the same connected components. So I can make that level n, I will have two components. Here I will have a z, say H0, here I have a z. Then if I increase, say I will have a bigger n, and these are the lattice points, say with weight less than 1, then this 0, and this is 1. No, they can be connected. And even, so say this is 1, 1, I will have here, say, disconnected component, but this one again will be, okay, here I made a mistake. Let's do it this way. Oh, sorry. That this is, it's born a new component which is not connected with that one. So here I will have somehow that this is my Sn. The Sn plus 1, some components will merge. Even if I'm just looking at the connected components, can be very interesting. So they merge, but some new components are created, and this is exactly the U action. Yes, yeah, I didn't define immediately. That is corresponds to the, say, to the inclusion of the Sns. So somehow I wanted to emphasize that these spaces as sense are very interesting, and usually it's not easy to compute them, even if we have, say, a Riemann expression or some quadratic function, or in the analytic is even more complicated weight function. To analyze this somehow, yes, our Z to solve these inequalities, and after that to see the agencies, yes, corresponding to the basis, to the EVs, it can be very, very arithmetical. Differential equation. So yes. So let's see now what is the definition. The definition of the lattice cohomology now is so again we have here I have the cubical decomposition, and we have for each n, for any n I have the space, for each n we have an Sn, we have the tower of Sns, and we define the lattice cohomology associated with the weight function and the lattice, the usual cohomology of Sn spaces in direct sum over n. Yes, so that is somehow the definition. That is exactly the definition. This has grading. Of course, that has a Q grading, because for each Q I have HQ. That is the Q grade. But also for each Q I have an additional grading corresponding to n, the Sn, S1, S2, S3. So the n homogeneous part is exactly corresponding to Sn. And if I have the tower, Sn includes, it's embedded in Sn plus 1, Sn in Sn plus 2, then in the corresponding cohomologies, we have the restriction map, and that is the U action. Yes. So in this, we have a grading and we have a U action. We can define somehow the grading if we wish, shift, and then also say multiply by 2 to have here minus 2 or something like that. We want to fit with the Heegaard Floer. But the point is that this is a graded ZU module for each fixed Q. We have the Q grading, and also we have for each Q a graded ZU module. In Q equals 0 case, we can do something more, because H0, the usual cohomology, splits. Yes, I fix a point and then splits the reduced cohomology plus Z. So according to this, starting from the minimum of the weight functions, you see, otherwise it's empty. Sn is empty. Starting from the minimum of the weights, something appears. So starting from there, we have a tower of Z's corresponding to this. If we add for each n, yes, we will have a tower of Z's, and we will have the direct sum of the reduced zero cohomologies. And this is called the reduced cohomology, reduced lattice cohomology associated with 0. And if Q is bigger, then as usual, the reduced cohomology is the same as the usual cohomology. Yes, as the HQ is HQ reduced if Q is bigger than 0. So for the reduced cohomology makes sense, and basically at H0 we have to be splitting, and this is the natural split. Actually, let's see that Sn is contractible. That means exactly that higher cohomologies we don't have anything, and in H0 we have just the Z. So that means exactly that the reduced lattice cohomology vanished. So in all our cases, what will happen that for n very big, Sn will be contractible. Yes. So somehow in a for finitely many n's, we will have some interesting information. Otherwise, it's the reduced cohomology is nothing. And so all the information, and that means also that the reduced lattice cohomology has a finite zero. And then we define the Euler characteristic somehow from the tower. We recover, or we keep the minimum of the weight, yes, weight function. And from the reduced part, which has finite cohomology, finite Z rank, we consider, as in the classical case, the alternating sum of the ranks of the cohomologies. Yes, so that is the Euler characteristic. So that was a general definition. Again, how we did. So we started with the lattice. And with a weight function with some finiteness properties. And then using this lattice construction and weighted lattices, using the Sn spaces and the cohomology of these Sn spaces, we define the cohomology of Evans spaces, we define the lattice cohomology. That is a very general set. We can see even combinatorial construction. The point is that if I choose different weight functions, say something defined topological level, then I get something. If I take a different weight function, I get different cohomologies. So let's see the very first one. Yeah, we still have time. So yes. So this is the topological lattice cohomology. So I defined this in 2005, 2008, a few articles. In 2005, only H0 was defined. 2008, all the cohomology was defined. So again, what is the setup? What is the starting object? I start with the link of a normal surface singularity, or I start with a resolution graph, yes, or the lattice of the resolution graph that is generated freely by EV. Yes, I have the standard basis EV, and we have even an intersection, a non-degenerate intersection, negative definite intersection 4, and then for I can take what just previously was the Riemann-Roch, but that is the generalized Riemann-Roch expression that I consider a characteristic element in the dual lattice. That is exactly, they are characterized by this property that we have this kx congruent with x square mod 2, and then we have, say, associated with this k, then we have a Riemann-Roch type expression that -1/2 L intersected with L plus k, where k is this characteristic element. If k is the canonical cycle, then we have the canonical, say, Riemann-Roch expression. Yes, and that is because of L is the intersection form is negative definite, with the negative minus sign here. I will have a positive definite form here, so that will have all the finiteness properties what we have. For the canonical, yes. So we won't know again. We have too many, yes, characteristic elements. But the point is that if I consider this, actually these are the species structures on X tilde. And then when I project somehow to the species structures to the link, then I have to factorize, and that somehow I have to make a choice. So what will be the choice here for each H? Yes, that is our index, what we want, the species structure of the link. I make a very special choice, yes, of I lift them, yes, to the dual lattice in such a way that it will be a minimal element. I forgot to write here minimal. That's the minimal element, and also in the anti-NF cone. Yes, so that is somehow that means that the Lippmann cone, if you are familiar with the notation, that in the anti-NF cone and minimal with this anti-NF cone condition, I have an element, and then I consider this characteristic element. So the point is that for every H of H1 of the link, I make a special choice of a characteristic element, yes, the characteristic element, and associated with that characteristic, I have a Riemann-Roch expression, and then I have a lattice cohomology. So for all the species structures of all the elements of H, we have a a graded ZU module. Of course, that this we can say that okay, it's nice. The point is that if you can do anything with it. In general, again, I repeat that it's very hard to compute because you have to analyze the lattice points and the agencies, or yes, of the lattice points, and then how they are compatible with the weight function. So it's by hand, it's not easy. Of course, that we have a lot of theorems and reduction theorems and the surgery formulas and what they have. So let's see what we can do with this. So again, for the link, that is the link of normal surface singularity, I take an H that provides me a canonical characteristic element and gives a weight function, Riemann-Roch expression, and we have a lattice cohomology. The first is that, of course, that here I use the resolution. I use the resolution, and if I take another resolution, then, okay, sorry, this was not the link. That is the lattice. Yes, that one here is the lattice, and that depends on the resolution. The first fact is that that is independent of the resolution. if I take, say, that the resolution, I blow up in several points, then these objects is independent of the blow up, so independent of the choice of resolution. So that is just an invariant of the three manifold and of the spin-C structure is indexed by H. And the second fact, and that is already shows that we are not very far from what we wish, that the Euler characteristic, again, that this is well-defined Euler characteristic, the reduced lattice cohomology is finite zero, has finite zero, and that so makes sense the Euler characteristic, and the Euler characteristic of this lattice, say topological lattice cohomology, is exactly the Seiberg-Witten invariant and shifted by that is the characteristic element associated with H. That is, we know that this is some kind of characteristic element in the case of links of singularities. That is some kind of second chain class or something. C1 squared, it's the analog of that one. That is the number of vertices. It's independent again of the resolution. So this basically, this is a good sign that we have our categorification of the Seiberg-Witten invariant, which is a new categorification. It's completely from the combinatorics of the link of the resolution graph or the plumbing graph. We can recover this lattice cohomology. Just I want to mention that the Heegaard Floer, the first definitions of the Heegaard Floer, and even all the other invariants, they are gauge theoretical definitions. They are not combinatorial. Later, for Heegaard Floer was proved that we can have a combinatorial definition, but this is completely combinatorial. If we take this weight function, then we have categorification of the Seiberg-Witten. So let's see some interesting. So how it's connected, say a little bit with the analytic invariant. So if I take, say, the canonical class and the classical Riemann rock, yes, associated with the lattice, then we have the following equivalent statements that X is rational in the sense of arting, that the geometric genus is zero. Yes, then that is equivalent with that all the spaces Sn are contractible. That means by the definition that the reduced lattice cohomology is zero. So that is exactly somehow this lattice cohomology characterized gives a new topological characterization of the vanishing of the geometric genus. Artin also has a topological characterization in terms of minimal cycle, but this is a completely different. Also, the elliptic singularities can be characterized. That is somewhere at the level, all the higher cohomologies are zero. At the level 0, I have some z's. So Sn, all the components of Sn are contractible, but I might have more components. And starting from S1, S2, S3, it's contractible. But S0, it's not contractible. I have more components. And also the weighted homogeneous case we can compute, and also that is H1, 2, 3, they are vanishing, and A0 can be very interesting, say, graded ZU module. Actually, in this case, I will not speak the connection with the Hodge theory. This conference is about Hodge theory, but here I can mention, for example, if I take a weighted homogeneous hypersurface singularity, then this information, what is in H0, that is equivalent with the spectral numbers. In more general case, I expect that there is a Hodge theoretical connection, but it's harder. We have to find it, but maybe it's not so easy because in this context they are not hypersurfaces. So it's even the Hodge theory, it's how to define. But I expect that this is connected with yes. Later I will come to the analytic part, and then really I expect that the analytic lattice cohomology will be related with the Hodge, some Hodge information. But again, I want, let's see one more example that for any Q, we can construct, say, we can construct a resolution graph or a normal surface singular topological type such that HQ is non-zero. So it's really some loops or two-dimensional cycles in Sn might appear. So for example, this is the that is an integral homology sphere. It's a negative definite. Actually, the link is this surgery manifold. And in this case, H1, it's non-zero. Actually, a loop appears, a very interesting loop appears. So that is in the lattice, the rank of the lattice is 7. And in this 7 rank lattice, somehow the Riemann expression and the lattice, it's very interesting combinatorics between them. And the spaces Sn are very interesting. Yes. So let's see again topological connection a little bit more. Again, we constructed the categorification of the Seiberg-Witten, and somehow the truth is that when I constructed this, I looked also on the analytic invariants that I wanted some of bounds and some connections. Actually, I hunted for the geometric genus, topological bounds for the geometric genus. And also, in some sense, I was at the later, when the Heegaard Floer was studied, and then also by the construction of Euler about the Heegaard Floer. And so let's see if we want to compare. And that again, it's a nice connection that is not totally independent. And then I will not define what is the meaning of bad vertices, but for example, in the star-shaped case, I have only one bad vertex, and that is the central vertex of a star-shaped graph that has only one bad vertex. And in that case, actually, I proved that the lattice cohomology defined, the topological lattice cohomology defined in this way, it's exactly, its isomorphic is the Heegaard Floer, the cohomological version of Heegaard Floer of Oswald and Sobol. And later, Oswald and Sobol and Stipschitz, they proved that if you have two bad vertices, then this isomorphism holds. Actually, it's not too complicated to explain what is the meaning of the bad vertices. So if you have a resolution graph, if I replace the Euler numbers, the self-intersection numbers, by something more negative everywhere, then I get a rational graph. Now the question is that in how many places I should decrease the Euler numbers. If it's enough only in one place, then I say that it's one bad vertex, and that is the definition. If it's enough to decrease at two places and I get a rational graph, then that is, we have two bad vertices. So in how many places we have to make some surgeries in the negative direction in such a way to hit a rational graph, yes, which are characterized topologically. And so that is the definition in the case of two bad vertices. Still, this is an isomorphism. And then we tried for many years to prove that in general, that was the conjecture I formulated, the conjecture that is all the time it's an isomorphic. And actually, Oswald, Sobol, and Stipschitz, they proved even the spectral sequence, the existence of a spectral sequence. And a few months ago, Zenke proved that indeed this isomorphism holds. So actually, in this way, we hit exactly the Heegaard Floer, the homological version of the lattice of the Heegaard Floer HF plus version by this construction. And maybe also a few words on analytic connection, that was the original motivation somehow to find upper bounds and then for PG. But no, let's concentrate again on the original question. That again, what we have now. So actually, here I have the Heegaard Floer in the previous question, but now I have something very precise, which is actually defined in the language of singularity series. So that is, I take a resolution, I take exactly somehow the Riemann expression. Yes, index somehow by the species structures. I make this construction, and at the Euler characteristic level, I hit the Seiberg-Witten. But what is interesting that this is somehow constructed in terms of singularity, in terms of resolution graph, though later we prove that it's independent of the resolution, but we have a good somehow tools to define this topological lattice cohomology. And the question is now, let's start with an analytic type. Yes, analytic type of for normal surface singularity, and we want an object here. So that's my question. That is our question now. So I hunted for many years to find out or to find this object. So I want somehow similar construction. Of course, they cannot be topological. I want completely different weight function here. So the lattice can be the same, of course. I can take the same lattice, but the weight function should reflect the analytic type. So using the analytic type of the normal surface singularity, I want to define here something which, of course, has some I can compare in nice cases or in all the time. Actually, that will be the truth that in any time we will be able to compare them. And also, I would like to have that the Euler characteristic of this lattice cohomology is the PG. And again, that is in equivalent version. Here, the equivalent geometric genus, and here it's indexed by the species structure and by H. Again, the link is rational homology sphere. We assume that, so the index set of the species structures over H is finite. So that is now the second step. And probably that second step, so that I continue tomorrow with that. So here is the analytic lattice cohomology, but that's tomorrow. So we continue tomorrow with the analytic lattice cohomology that we associated with the analytic type. And then we compare the topological lattice cohomology with the analytic lattice cohomology. I want to convince you that this lattice cohomology, the analytic lattice cohomology, depends on the analytic structure. If I fix the topological type and if I move the different analytic structures on that fixed topological type, then even the cohomology might jump. And then with that one, we want some information about the possible, say, the stratification of the analytic moduli of this fixed topological type. And also some other interesting, so how it behaves with respect to the flat deformation and this kind of questions. And also the analytic lattice cohomology, I will extend, I don't know if we will have time, to any dimension. So it will be a very nice construction which fits with, so it's independent of the dimension. So thank you, this I stop here.
I'd like to thank the speaker for a very nice talk. And so if there are any questions or comments?
Yes, I have a question. So in addition to Seiberg-Witten and Heegaard Floer
Yes.
homology, we also have instant-on Floer homology.
Yes.
Do you
yes.
have any hope of recovering that from?
Hope we always have, but you see, this is yes. So that's a good question, and we have to try. So no, that's somehow the project to try to, and actually that should work because that is yes, that is the categorification something of the Casson, yes, and Casson.
Yes.
So and this is here I have the Turaev torsion, yes, and then basically Turaev plus the Casson Walker. And this is somehow no hit to the Seiberg-Witten, but also for the other one, it's a very good question, very interesting project. I would be happy to work on it, of course, and yes, and so we can make similar question that we list couple of topological invariants already known and studied, interesting, very important topological, that if we can construct the analog, we have analog construction at topological level. And also then we can ask that what is, say, the analytic version of the instanton, yes? And
yes.
That is even more interesting that, yes? And then what is the Euler character, what is beautiful projects, and yes, beautiful. I would be happy to work on that.
So I expect that in addition to the resolution of singularity, a Milnor fiber will make an appearance.
Yeah, you have to fix, you see, yeah.
Okay.
Okay, thank you. Any further questions?
So may I ask you?
Sure.
Yes, so I would like to ask you about the spectral numbers.
Special numbers?
You mentioned the spectral numbers.
Spectral numbers, yeah. So you see, actually there is you see, so I cannot connect, that was my hope and I really wish, but of course there are some obstructions, some problems here that the spectral numbers say the Seiberg or the mixture structure of the Milnor or the vanishing cohomology is defined only when we have Milnor, when we have vanishing cohomology. So say hypersurfaces or even more general, but And in that case, we have the monodromy and we have the spectral numbers. Now, in some cases, I computed, say in the weighted homogeneous case, or even in the Newton non-degenerate case, I can compare the hypersurfaces and say in this case, and in those cases, I really see the connection. So the weighted homogeneous case, actually this information somehow, if you know the spectral number, somehow you have a recipe how to recover H0, lattice cohomology H0, and also converse. So basically the same information, but of course that somehow the weighted homogeneous case is not the most, it's somehow in the weighted homogeneous case, almost all the invariants are the same. Yes, and so the spectrum and then also the Poincare is the Pinkham formula is the same, yes, so it's a lot of expressions, analytic or topological, they agree. And actually this is a good sign that also this gives the very same information. In more general cases, I don't know, so it would be very interesting again, I don't know the answer, but for hypersurface, yes, from C3 to go to 3, and you have a, say, vanishing cohomology, and you have the spectrum, then if that one can be connected with this lattice cohomology, how it is, and then if that what that recipe what for weighted homogeneous case works, if it can be extended. It's a beautiful question. It's a good project again. I'm sorry, but and I'm sure that if the weighted homogeneous case hits perfectly, then even in later in the more complicated cases, some connection should exist. So, but we have to find exactly the. So I will be happy to discuss about it.
Thank you.
Okay.
But you see, it's a just sorry for the video that here somehow in the hypersurface is somehow how we define the spectrum. We define as an embedded invariant in C3 how we deform, yes, and here all this business was defined as an abstract normal surface inverted, non-embedded. So it's also appears an additional. If something comes out, then will be very interesting because we'll be connected with the abstract analytic type of the X and the embedded, say, analytic. Of course, that in the case of hypersurfaces, it's not a big distance, but still it's.
Okay, thank you. Any further questions? If not, I'd like to again thank the speaker. Our next talk is at 1:30.